Okay, so time to get started. So real quick before we get into the math, just a reminder. So y'all heard me say and you read on the website that attendance will count as part of the grade. You may have also noticed I have not been calling attendance for the first couple of weeks of classes here. And that's because the class roster has been in flux and it just doesn't make any sense. But that should be solidifying pretty much this week. And so we are going to start counting attendance. I'll be calling names, hopefully learning faces as I call names and people identify themselves, and eventually I'll just be able to do it visually. It usually takes about half a semester for me to get competent with. But anyway, that will begin on Wednesday. So just FYI, officially notified now. And so anyway, make sure to come to class. And there's a bunch more discussion on the website, of course, as to exact details and how it counts to the grade, and et cetera, et cetera. Okay, so last time we were talking about various different categories of questions where you want to compute distances. The last example that we looked at was how to find the distance between parallel planes, and the big idea is that even though you could pick a couple of points and talk about the distance between those 2 points, that's not what we're talking about, right? We want the perpendicular distance, the shortest possible distance. And so the easy fix, no problem, is to say, well, look at that difference vector. Again, pick any 2 points, doesn't matter, and then look at the component in the normal direction. And that component in the normal direction is going to, that's about like so, right, is going to give you the distance. Now, the one little asterisk is, of course, distances are intrinsically positive things. Components are not. Components might be negative, right? If the vector and the normal vector are going the opposite directions, we still want a positive distance. It'll compute that as it's negative. So don't forget to take the absolute values. Okay. All right, so this is where we left off last time, and we were almost done with this section. One last example to show you is the distance between 2 skew lines. Now, skew means that they don't intersect and they are not parallel. The way I like to think about this is skew means that the 2 lines, they have nothing in common. No points in common. They don't have a direction in common. Just nothing in common. Okay, so how do you find the distance between 2 skew lines? In particular, let's say it'd be something kind of like that, maybe. How are you going to find that distance? First of all, let's be clear again on what do we mean by the distance. I don't mean pick any 2 random points. I also don't mean pick any point on one line and look at all of the other points on the other line and then pick whichever is the shortest of these. I don't mean that either. Right? So you have to consider over all possible points on the one line and all possible points on the other line. Right? And what we're going to be looking for is the pair of points such that the line segment between them is perpendicular to the first line and also perpendicular to the second line. Okay, so that's what we mean by the distance between 2 skew lines. Okay, so how to find it? Turns out all we have to do is turn this question into a previously solved problem. And by the way, another, there's a long and proud tradition in math of turning questions into other questions that we already know the answer to. Right? So that's what we're going to do here. The big realization is to note that if you have 2 skew lines, those 2 skew lines can be thought of as being in parallel planes. Whenever you have 2 skew lines, there's always a pair of parallel planes where the one plane contains the one line and the other plane contains the other line. Now, how do I know that's true? Well, the neat trick to make that realization is to just take the 2 direction vectors for the original 2 lines and just cross them. Right? When you cross those 2 direction vectors, the result I know is perpendicular to both of those two direction vectors. And that's going to be then the direction vector for my two planes. So you just pick a point. It doesn't really matter which one. Once you have this normal vector, you can pick a point in one of these lines and then ask the question, where is the plane that contains the given point, and that is perpendicular to the given normal vector, and that will give you this plane right here, and that will contain that line, and then likewise for the other one. Okay. So, then what do you do? Right? And here's the kind of the beauty of this transition, right? I've turned the question of find the distance between two skew lines. I've turned that now effectively into the question, how do I find the distance between two parallel planes? And I already know the answer to that question. Right? So we've turned a new question into an old question. And same solution as before. Okay, so it's a real slick move, real clever. Wish I'd thought of it. How we doing? Is everybody on board? Okay. Yeah.
I have a question. If the skew lines are like parallel, so
that's not skew though.
If the two lines are parallel, I'm trying to find the distance between.
Oh yeah. Okay. So then that's a different question, and so that's a trickier question. Well, it's a different question. What I would do with two parallel lines. And presumably I have points given in these parallel lines, and presumably have a direction vector parallel to these parallel lines. And I would then say, okay, well, I've got the one vector, and I also have this difference vector here, right? And then I can cross them, and that'll give me a normal vector for a plane containing both. Right, and then let's see here. What are we going to do with that? And then I could cross these two to get the perpendicular vector, and then there you go. So you see, it's a game, right? And you got to kind of look at the geometry, think about the moves that you have, the tools you have in your toolbox, and just keep playing the game until you win the game. Yeah. Okay. Yeah.
When you draw the plane, are you assuming they're parallel or like?
Yeah, his question assumes that the lines were parallel. Yeah, exactly. And if they're not parallel, then they're skew, and that's the other one that we already did. Yeah. Okay. There's a million versions of these kinds of questions, and so again, I can't show you the solutions to all of them, but I want you to see the big picture strategy of geometrically tinkering, basically. Yeah.
For the question above, why do you use the components and not the length of the projection?
Same thing. The absolute value of the component is the length of the projection. Okay. So yeah, you could do it that way. It's I think slightly more computationally. You're creating a vector only to then decide that you only want the magnitude of the vector. So I think it's more work for the same benefit. Okay. Yep. Okay. So moving along. Section 1.7 now. This is, I just need to make sure y'all are aware of the basic ins and outs of a couple of new coordinate systems that are in common use for really, really good reasons. There's things that you just can't do very well with rectangular coordinates. So let's start off by talking about what are rectangular coordinates. The rectangular coordinate system. And what it is given a point, right? Given a point in the plane, then we talk about the x-coordinate by, draw this little rectangle, or multiple different equivalent ways to think about this, right? But you get an x-coordinate and you get a y-coordinate, and between the two of them, we call these the rectangular coordinates for that point. So given any point, there is exactly one set of rectangular coordinates. And given any set of rectangular coordinates, of course, there's exactly one point. So this leads to the first observation I want to make about why I like rectangular coordinates, and that is that rectangular coordinates are unique. For a given point, there is exactly one set of rectangular coordinates. Couple other nice observations I'll make. Here's a pretty sweet one right here. This formula that you all presumably remember from linear algebra. If you have the coordinates of a point, those are the coefficients in a linear combination of the standard basis vectors that produces that same point. Handy, right? That's awfully useful, and presumably you've used it a million times in linear algebra, and we will use this a million times in this class as well. This, of course, is just a special case of a broader fact, and that is that coordinates, you might say linear combinations can be computed by coordinates. So if you're taking a linear combination of two vectors, you can compute the coordinates of the result by taking the same linear combination of the corresponding coordinates. That's really handy. And again, you've used this a million times, presumably. Okay. So why do we bring this up? And that is that tragically, all of this that we've talked about, right, fails in these new coordinate systems that we're going to talk about. So these are things you're going to have to let go of, right? And so FYI. Okay, so let's get going with new coordinate systems. I'm going to start with polar coordinates. Some of y'all may have seen this before. I imagine probably a lot of you, if not most of you, have seen this before. There are different ways to think about it. I'm going to present this what I think is the best way for our course-wide purposes, and that is to think of polar coordinates as being a function. The big idea is that if you give me an r and a theta, and I can think of those as defining a point, I'm going to call it r comma theta in the r theta axis system, right? If you give me an r and a theta, I can use theta as follows. I'm going to let theta define a direction by rotating counterclockwise from the positive part of the x-axis. And with that direction established, I'm going to let r tell me, I'm going to air quote, how far to go in that direction. So I do want to be careful about that. When I say how far, emphasis on the air quotes here, again, we have this issue about the difference between a distance and a scalar. And I know it seems like a triviality, right? But it's an important distinction because distances are unavoidably positive, while coordinates are not, right? And importantly, r is a coordinate; it's not a distance, right? So how far in quotes, because it could be negative, by which I mean if r were negative, we would just go the other way. And let me clean up the picture so I can do that. Given a given value of theta, if r is positive, you go that way. If r is negative, you just go the other way. Like that. Is that cool? Everybody happy? Okay. Alrighty. And with that stated, I'll point out that we have a right triangle there, and y'all may recall the trig of right triangle. So you can look at that right triangle, you can immediately recognize that x is r cosine theta, and likewise y is r sine theta. So now do make sure that you're crisply, unambiguously clear on exactly how that works. Think about the triangle sines and cosines and make sure you're solid on that. Please also do make sure that you memorize these formulas, that x and y are like so, because that's going to come up a million times in this class. Everybody good so far? Okay. Right. So now, why am I insisting on thinking of this as a function? Right? Why get all upset about this is kind of an awkward way to think of coordinates, right? It's tempting to say that for a given point, just look at the value of theta and look at the value of r. The problem is There is not a single value of theta that will get me to that point. And there is not just a single value of r that will get me to that point. Right? So here's the awkward reality. Now, just as an example, here's a point in the xy plane, and I'm going to notice that if I look at that angle as being, some value of theta, whatever, and then if I look at this distance, apparently I've chosen this distance here to be 5, and so the polar coordinate function takes that point to that point, r and theta, the usual rules. But here's the thing. This up here, where I add, wrong color, where I add 2 pi to the value of theta. Now keep in mind, if you add 2 pi to the value of theta, that just means do a full turn. And the result then is for this value of theta, it's technically not the same theta, but it does get me pointing in the same direction. And that'll get me to the exact same point. Right? So polar coordinates are not unique. It's a one-way deal. Right? If you give me polar coordinates, that defines a point. If you give me a point, there's lots of polar coordinates. So you can't talk about the polar coordinates for a point. All right. Now let's see here. Here's a different observation that we can make. If instead of adding 2 pi, what if I add 1 pi and look at this direction? 1 pi means I'm going to do a half turn. And a half turn then will have me going in exactly the wrong direction. And now again, let's think through geometrically, right? If you're going in exactly the wrong direction, you can just go in that wrong direction backwards, and it gets you to the same point, right? So the negative value of r, so minus 5 then, again gets you to that same point. Like so. So heads up, right? Be aware that awkwardly there's tons and tons of different polar coordinates for a given point. Alrighty, so moving along. You do have to be careful with your notation. Our own book, in fact, is just a skosh sloppy on this. Forgivably, there's no ambiguity. I was not misled by anything the book wrote, right? But technically, there's an ambiguity in how sometimes, in lots of contexts, people are a little bit vague about how they write things. So, for example, 2 pi over 6. Now, most reasonable people would look at this and think, okay, well, you know what, that pi over 6, it looks like an angle. Right? So presumably this is an r comma theta. And yet, 2 is a real number that could totally be x, and pi over 6, weird though it might seem, it is just a real number, and that could also be y. So technically, this could refer to, the r comma theta, or it could refer to the x comma y, and these are different points, and it is not clear which one of these that means. So anyway, just heads up, something to think about. Try to always head on a swivel, think about the context, make sure that it's clear. If you've already established elsewhere in your work, that you're talking about polar coordinates, then that's fine. Otherwise, notice how easy it is to clarify. Just a little bit of extra notation here. Just say r comma theta equals 2 pi over 6. Ambiguity gone. Perfectly. Everybody happy? Okay. Here's one that a lot of students mess up. Y'all have probably either seen or can think about a little bit of geometry and trig of the usual right triangle, and see these formulas right here. Right, we have the Pythagorean identity, effectively there, And we have just the kind of the definition of tangent here, right? No big deal. Beware the temptation to write down instead. Let's see here. It's tempting to write r equals square root of x squared plus y squared. But this is not always the case. So I'm going to put a big X through this, just because that's not always right. Because this symbol, right, the square root symbol, does not mean whichever square root might be more convenient for your purposes, right, because there are, after all, two square roots. That is not what this symbol means. This symbol means the positive square root of whichever number is underneath the radical. So this equation that I've just crossed out would imply that r is always positive, and that's not true. Right? Okay, so don't do that. Likewise, it is tempting to say theta is arctan of y over x. And again, that's also not true, because arctan only takes certain values, right? The arctan of some proportion y over x is not every possible angle whose tangent is that value. No, it's a specific value. Arctan is a well-defined function. And that would suggest a constraint on the allowed values of theta, which is not true. So again, heads up on that. Don't do that either. Now, just for the moment, just to illustrate an additional problem that this can lead to, I'm going to unscratch these formulas. I'll scratch them out again momentarily. Let me see if I can scratch these out competently. This is going to be a tricky one. I guess there we go. Okay. So what would happen if I used these formulas to try to understand this point, -1 comma -1? All right, so -1, -1, here it is. And by the way, easy to compute r squared, easy to compute tan theta, just using these formulas right here. Perfectly fine, right? But then here's the deal. If you were mistakenly to use these formulas up here, well, you can just take the square root of the r squared and the arctan of the blah blah, and what you would conclude is that this, well, in fact, here, let me be a little bit more careful. You would conclude that r would be square root of 2, and theta would be pi over 4, which would put you over here, which is wrong. Right? Now, let me emphasize, I didn't pick some obscure, transcendental numbers or, some weird, anomalous, hardly ever happens in the real world scenario to get these formulas to crash and burn. -1, -1. This is innocent, simple little numbers. These formulas crash and burn. Everybody see that? For dramatic effect, right? So please do not use those formulas. They're just not true. What you have to do instead is look at the different possibilities. Let's see here. Let me go ahead and erase the garbage. Let's get rid of all of this that I hopefully have persuaded you against by now. Let's notice that this formula implies two different possible values for r, right? And then this formula here implies, I'm going to say two different possible values of theta, but all right, I mean arctan, there's a bunch of, it's a periodic function. You can add any multiple of 2 pi, nothing happens, right? But so nevertheless, there are still kind of like, well, there's that direction and there's that direction, represented by these two sort of groups, you might say, of thetas. So once you write that down, how do you tell which way to go? Geometry, right? Don't try to rely on algebra to do this for you. It's a mistake. Now, that's not to say that you can't create a set of rules and a little algorithm that you could memorize that would get this right every time. And yeah, I suppose you could, but I think that's a mistake because you're going to misremember your algorithm. Question of time, right? What will never lead you wrong is to just think carefully about, well, what do these values of theta, which way do these thetas point? Are they pointing the right way? Are they pointing the wrong way? You know where your point is, -1, you can see it, right? So let geometry be your guide, yeah.
What is positive versus negative r represent in the graph?
So if r is positive, that says you're going to go that distance in the direction that theta would have you point. Negative means go backwards. Yeah, right. Yeah. Yes?
Yeah, for polar coordinates, are they only like valid in R2?
Correct. Polar coordinates is only a thing in R2. Yeah. Now there's a three-dimensional kind of analog of this, and we'll talk about that in a couple minutes. Yeah. Yeah. Okay. Okay, so always think through the geometry, and let's see here, let me clean up the huge mess real quick. And so, for example, if I look at pi over 4, that suggests that way. Don't forget my point is here, and now I ask to my geometric intuition, hey, intuition, is the point actually in that direction, or do I need to go backwards to get to this point? Perfectly obvious from the picture. For my geometric intuition, clearly I need to go opposite, which means that I will pick, where's my color? Here it is, minus pi over 2. I'm sorry, minus square root of 2 for my r there. Everybody happy? All right. Or, of course, you have the other option, which is to choose this angle, which is that way, and geometric intuition there tells me positive square root of 2. So don't negotiate away the role of your geometric intuition in trying to make sense out of these formulas. Okay. Alrighty. Moving along. A couple of quickie equation conversions. So here we have a polar equation, and now it's not hard to persuade yourself that that is a circle. After all, it's straight up telling you that the distance from the origin has to be 3, and of course that's going to be a circle. But let's suppose you hadn't noticed that. Check it out. If you square both sides, then we get an expression that's familiar. Here we go. Yeah. We get an expression that I can easily turn into rectangular coordinates. That's a handy little trick, right? So having made that connection, then what I get is that my polar equation has now turned into a rectangular equation. And again, if I hadn't immediately understood how to deal with that polar equation, the rectangular equation, more familiar and allows me to, I want this, okay, there we go. Allows me to see what it looks like. Okay. Likewise, now what if you have theta given as some value? Now don't square both sides. Theta squared is not something I have a formula for how to rewrite in rectangular coordinates. But I can take the tangent of both sides, and tan theta is a different expression that I have a pat formula for how to turn into rectangular coordinates. Handy dandy. Let me momentarily skip over this next example and come to the fourth example on the page here, r equals cosine theta. You're going to see this r. You're going to be tempted to square both sides and get that r squared that you can, conveniently rewrite in rectangular. The problem is if you square both sides, the other side of the equation will turn into cosine squared. Again, not really a thing, right? I don't know what to do with that. So the different move here. And again, tool for your toolbox, it's just kind of good to have been down the road of a couple of different weird examples and just kind of see what works most conveniently. Multiply both sides by r. That's just a tricky little trick that happens to work in this case. And multiply both sides by r, and the result is that is something I recognize, and this is something I recognize. And now I have a rectangular equation, and now I can get down to the more familiar business of how do I understand that equation. And I'm just going to make a real quick reference for y'all, completing the square. You may have heard of completing the square way back when, what they used to call Algebra 2 when I was in school. I'm sure it's called something different now. But it's a neat trick. A lot of people have been misled into believe that you don't need completing the square if you've already memorized the quadratic equation. That's only one use of completing the square. Completing the square is useful in other situations, such as this one. And so the big idea in this case is to take the original equation with terms moved around a little bit and realize that adding a 1/4 to both sides is exactly the little clever trick I need to turn this into a perfect square. Right now, if you're not proficient with completing the square, and how did I know it was going to be 1/4? Google it, right? Look it up. It's a standard move of algebra. Anyway, make sure that you're proficient with completing the square. It comes up often enough that I think anyone taking a class like this really should make sure you know how to do that. Okay. And, of course, then the nice punchline is we recognize this as a circle like so. Okay. Alrighty. And then here's a very similar example. And, again, I can take the rectangular equation. This is going the other way, I suppose. But I can take a rectangular equation and I can rewrite rectangular into polar instead of polar to rectangular. And the good news is, when you're going rectangular to polar, I'm going to say it's kind of easier. What I mean by that is you can always just kind of plug in your conversion formulas. Y will always be r sine theta. You just write it down. Right? And you can do the same thing throughout the entire equation. Now, I advise that you look out for handy little shortcuts. For example, if you can kind of see this coming, right? And so I see the x squared. I anticipate a y squared. I kind of see this coming. Go ahead and expand that out first before you start plugging in trig. Because then that, again, being something you immediately recognize, you can simplify much more easily and save yourself just a little bit of unnecessary trig and trig-related ugliness. So, neat trick. Okay, how we doing? Everybody happy? Again, a circle, thus the connection to the previous example. Something to be on the lookout for, pay attention to, is that notice both of these examples give circles. One of them involved cosine, one of them involved sine. Right? And you could probably imagine that, by the way, notice that there's a 2 out in front in this equation, and notice further that the radius and the center also twice as big as the radius and center over here. So, roughly speaking, there's a whole sort of family of circles with centers on the x-axis, tangent to the y-axis at the origin, that all fit roughly that form over there with just different constants in front, and likewise over here on the y-axis with sine instead of cosine. So, kind of neat observation. Okay. All right, back up to the one we skipped. Sometimes there's just no particularly convenient algebraic trickery to help you understand what you're dealing with. And again, sometimes you got to get your hands dirty. So here we go. Let's look at this curve right here. R equals sine of 2 theta. And I don't think there's any convenient way to write this in rectangular coordinates. Try as you might. So if we want to know what this looks like, we just have to point plot. And instead of doing that literally one point at a time, it'd take forever, right? I like kind of doing ranges of angles all at once. And so, for example, let's consider all of these angles here. Now, of course, that's theta equals 0 to theta equals pi over 2. That's that range of angles, right? Keeping in mind that is the range of values of theta. Further notice, theta is not what I'm taking the sine of. What I'm taking the sine of is 2 theta. That means the argument doesn't go from 0 to pi over 2. The argument of sine goes from 0 to pi. And with that established, for this range of values of theta then, you can see that r is going to start at 0 and then increase up to 1 and then decrease back down to 0. And so now I'm going to literally, just in polar coordinates, trace out what I've determined here for these, and I'll see here, for these values of theta starting at 0 and eventually rotating its way up to pi over 2. For these thetas, I'm going to start with 0 as my r, and then I'm going to slowly increase my r's, and then I'm going to decrease symmetrically back down to 0. And as I do that, as I rotate through these directions, we get something kind of like that. And that then gives me a plot of my curve, right? My curve kind of, oh, okay, well that was not good. Let's see, let's try that again. Goes kind of like that. Everybody with me? Okay. And I'm going to say et cetera, but let me start you off on the next set of values of theta. Let's think now about these values of theta from pi over 2 to pi. Keep in mind that's what theta is doing. The argument of sine is twice that. The argument of the sine function goes from pi to 2 pi, over which r itself starts at 0, goes negative down to -1, and then comes back up to 0. Now this one's a little bit confusing to plot through because as I look at these directions, I'm going to be going negative amounts in that direction. So even though my theta is pointing that way, my points are going to be kind of back over this way. So starting with, for example, a direction kind of like that, I'll be doing a negative value of r. Again, as previously noted, negative values of r, so moving backwards from that direction, and that would put me about right there. And likewise for all the other directions, and you can persuade yourself that I'll do something kind of like that. Right, and so my original plot that started off like this continues on like that. Everybody okay? I mean, there's a bunch to digest here. Keep in mind, all this is being recorded, and so if you need to listen to this again and pause it and think it through and rewind and listen to it again, et cetera, take time as necessary to make sure you're comfortable with this strategy and these ideas here. Okay, so let's see here. We're good on time. Cylindrical coordinates. This is actually a kind of a quick one. Cylindrical coordinates is pretty much just polar coordinates in 3 dimensions. Some people call it literally polar coordinates in 3 dimensions. Some people even just call it polar coordinates, and it's just kind of understood that it's in 3D. I think that's unfortunate. It is, as a whole, as a coordinate system, if you're in 3 dimensions, this is not exactly the same as polar coordinates. There is a third coordinate. Polar coordinates doesn't have that. There's no need to reuse that term polar coordinates as a perfectly convenient term to use to make the distinction. We use the term cylindrical coordinates. So I think this is the best thing to call it. But yeah, it is actually very, very closely related to polar coordinates because whatever your point is, that you want to write down the cylindrical coordinates for, the very first thing you're going to do is just look at the projection into the xy plane, and then in the xy plane, you're just going to write down polar coordinates, for which the relationships are exactly what they were in 2 dimensions, because that projection is in the xy plane. It's exactly the same, right, in terms of those formulas. That's pretty convenient. The only thing that's left to be thought about is the remaining coordinate, which of course is just z. And so cylindrical coordinates doesn't do anything with that at all. It just leaves z as z. So you might think of this as polar coordinates, comma z, right? Perfectly reasonable, no problem. All right, so a couple of quick examples. Let me do it like this. This equation right here, r equals a constant. If you think about it, in polar coordinates, r equals a constant gives you a circle. In cylindrical coordinates, r equals a constant gives you a circle for every value of z, and so it makes a cylinder. So let me try to do a better artistic job here. Yeah, makes a cylinder, and thus the name cylindrical coordinates. Everybody good? Okay. Yeah.
Why not, like, I don't know, this is just like an idea, but like instead of z, do like another angle, and then you move in like that.
Yeah. Well, there are other coordinate systems that one could. There's an endless supply of alternative, different coordinate systems. For the moment, I want to talk about cylindrical coordinates. Yeah, there is the very next one we're going to do is called spherical coordinates, and it might be kind of what you're thinking of. We'll see on the next page. But then there's more than that. Yeah, for the moment, yeah. All right. Let's see here. So what about a sphere? There's a sphere centered at the origin. How would I write the equation of the sphere in cylindrical coordinates? Well, in cylindrical coordinates, I've kind of got to get rid of x's and y's. I can keep the z. Z is a cylindrical coordinate. That's cool. I don't even have to do anything with that. That's fine. But I do need to get rid of the x and y. X and y are not cylindrical coordinates. And I got to rewrite x and y in terms of r and theta. Now, again, you can plug in the trig, or you could just kind of notice that that's, again, one of our pat conversion formulas between rectangular and polar. And thus, notice we have what you might call the cylindrical equation for a sphere. All right. Okay, here's another example. Here we go. Z equals KR. What are we going to do with this right here? What does that look like? There's different ways that you can think about this. I'm going to show you my favorite way. Let's see here, color choices. First thing I'm going to observe in this equation here, there's no thetas in that equation. How about that? You remember how we, when we were talking about lines and planes, I made this observation. Hey, if there's no y's in the equation of a plane, geometric conclusion. It's parallel to the y-axis, and we walk through a justification, right? There's a different geometric conclusion here. If there's no thetas in your equation, I argue that the absence of theta means that whatever theta is, whatever theta slice you might be looking at, well, there's no thetas in the equation, so when you change the value of theta, nothing happens. That means all the cross sections in all of these theta slices, they all look exactly the same, which means it's rotationally symmetric around the z-axis. And again, very powerful geometric conclusion from a casual glance at the equation. right? And you gotta love it when that happens, right? So easy freebie. When you notice there's no thetas in your cylindrical equation, rotationally symmetric. And if you want to understand something that's rotationally symmetric, you only need to understand any single cross section. It doesn't matter which one. So, for example, I could look at, this value of theta, whatever that value of theta is. Right? Pick a theta. Who cares? They're all the same. And see what r as a function of theta looks like for that value of theta. And this is easy. I mean, z equals kr. Okay, that's a straight line. Right? Z is a function of r. Straight line. Now, tempting to stop here, but do keep in mind z is perfectly allowed to be negative. R is perfectly allowed to be negative. So you actually need the whole kind of line there, and that entire line, let's see if I can draw this reasonably accurately from there down, so a point up there and a point down here, if you will. That whole thing, imagine what that generates as that rotates around the z-axis, and of course that's going to make this cone. Like so. Everybody good? It's a neat trick. Okay. Alrighty. Spheric. Oh, you know what? I got ahead of myself. So, yeah, I do want to warn you about one quick thing. You do have to be careful with the letter R going forward. If you're in rectangular coordinates, and if you're fixed, dedicated, no way out, you're gonna guarantee stick with rectangular coordinates, then R is just another letter of the alphabet, and it's kind of convenient to use R to represent the radius of whatever you might be looking at, and that's nice, right? But if there's a reasonable chance, possible interpretation that you might be using polar coordinates or cylindrical coordinates, then all of a sudden R is now a coordinate. And you can't use R to represent a constant that plays a role in your picture if it has to be a coordinate playing a role in your picture. Think about it this way: if you were in a high school algebra class, I'm going to be talking about a circle and a line and a whatever, some geometry. Would you call the radius of that circle x? No, of course not. Absolutely, that wouldn't make any sense. X is a coordinate. You got to leave x free to play that role for arbitrary points that you might be solving for. It's a coordinate, not a constant. And so likewise here, R is now a coordinate, not a constant. You cannot use little r to represent a constant. So now what you can do is choose from a wide variety of other options. So for example, if you want to use R naught, that's perfectly fine. Right? If you want to use capital R, cool. All good. If you want to use R tilde, okay, fine. Right? So plenty of options available. You just can't use R. Okay. Alrighty. Moving along. Let's see here. So real quick, I guess I'll get us started on, let me just check the time real quick. Yeah, we got a minute and a half. I want to just kind of start the ball rolling on spherical coordinates. There we go. So the big idea of spherical coordinates is to kind of copy theta. This is the same theta from cylindrical. But then to take it in a totally different direction from here. If this were cylindrical coordinates, we'd be talking about r, that distance in the projection, blah, blah, and that is not how spherical coordinates works. Spherical coordinates says next thing we're going to do is look at the angle off of the positive part of the z-axis, specifically off the positive part of the z-axis and toward the theta direction. Right? So your theta defines this half plane that I have highlighted in green there, and then phi, this angle called phi, tells you how far to lean into that plane from straight up. And between the two of them, then that defines a direction. And now let me clean up my mess here. The two of these together define a direction. Man. And once you have a direction, then there's just a question of how far do you go in that direction, and how far, again, in quotes, could be negative, but how far tells you then a point. And so this trio, theta, phi, and rho, is what we call spherical coordinates for that point. And I'm bound to be out of time by now, so yeah, let's go ahead and call it a day right here. And yeah, see you later. By the way, I noticed this is the first Monday of the semester, so good luck with your first Monday. See you later.
Yeah,